Okay, so having seen the results of this section, we are now ready to solve the exercises. And this is the first one. We have to prove that the annihilator of W is a subspace of the dual space of V, where W of course is a subspace of V. And we already have solved this when we were going through the theory part. There itself we solved this. So let's see this next one. Here V is of course a vector space and S is a subset of V, any subset of V. Now just like we defined the annihilator of a subspace, we can also define a similar thing for a subset S. Similarly, that is, A of S is the set of those linear functionals f that make the entire S vanish, in this sense that if you apply f to any element from S, then you get the 0 vector in V. So we then have to prove that this A of S is actually nothing but A of L of S, where L of S is the linear span of S. Now L of S is, we already know, is a subspace of V. So this A of L of S is something we already have even before this general definition of A of S. So these two should be equal. That's what we have to show. So let's see the solution. We take care of one trivial case first, namely when S is the empty set. Note that what is this? By definition, if we just simply blindly use the definition, I mean we write the set and then we will see what it ultimately becomes. It is by definition the set of those linear functionals such that S, f, the f image of S is equal to 0 for all S belonging to the empty set. Now let's look at this condition more closely. This thing, this statement that SF equals 0 for all S belonging to the empty set can also be written slightly differently like this. If S is an element in the empty set, then the f image of S is 0, and this statement is vacuously true because it's after all an implication. In the implication form you would just write S belongs to the empty set implies SF is equal to 0. In this implication the hypothesis is false, so it's vacuously true. It's true nonetheless. That means irrespective of our choice of F, actually this is always true. That means, in other words, this is true for all linear functionals f, and as such this set has all the linear functionals, that is, it is the entire dual space V hat. Also, okay, now we calculate this when S is the empty set. Also, the annihilator of the linear span of the empty set. We already know what this linear span is. It's the trivial vector space consisting of only the 0 vector. Again, we apply our definition in this case also. Such that SF is equal to 0 for all S belonging to the 0 space. but there is only one vector in the 0 space, namely 0 itself, and 0 is mapped by every linear functional onto itself. That is one of the properties of linear functionals. In fact, it's a property of a general linear transformation also. So that is why here also all the linear functionals will be there. So this is also phi hat. So in this case they are in fact equal. Now assume that S is non-empty. So the empty part we have handled. So now we can assume that S is non-empty. S is non-empty. Since S is a subset of the linear span of S. This is something we already know. We have annihilator of the linear span of S, a subset of the annihilator of S. But why and exactly how is this following from this? It's very easy to see. You see, the annihilator of A of S is what? It is the set of all linear functionals such that Vf is equal to 0 for all V belonging to L of S. By definition, this is what annihilator of L of S is. So that means this is important for all V belonging to L of S. Now because S is a part of this L of S, so in particular for all V belonging to S also this will be true. In other words, every such F that belongs to this set also belongs to the annihilator of S, and that is why we are having this, and the containment gets reversed. If you think of it this way, this comes here and this goes there. Now we have to prove that the reverse containment is also true. So for the reverse containment, we take an element here. Let F belong to the annihilator of S. Now we have to prove that F also belongs to the annihilator of L of S. For that, we need to show that F makes every vector in L of S vanish. Let V be any vector in the linear span of S. Then V is a linear combination of some elements in S with coefficients, scalars coming from the underlying field. It's already there, we understand that. V is the linear span, say alpha 1 S1 plus alpha 2 S2 plus alpha n Sn for some positive integer n. Note that this fact that V being in L of S implies V is a linear span of some elements of S is true only when S is non-empty. When S is empty, of course this does not make sense, and it's also not true. So that is why I handled the empty case separately. But anyway, now we have this. Since F belongs to A of S, so all these Si's will vanish under F. That is SIF equals 0 for all I from 1 through n. Hence, VF is alpha 1 S1 plus alpha 2 S2 and so on alpha n Sn F, because F is after all a linear transformation, a vector space homomorphism, so we get this S1F plus alpha 2 S2F plus alpha n SNF, and these are all equal to the 0 vector in V. This is 0. So just like F makes the entire S vanish, it also makes the entire L of S vanish. This implies that F belongs to the annihilator of the linear span of S. So this is also a subset of this, and then you can combine these two containments to have equality, and that just completes the solution. Ideally, you should not just simply leave it like this. You should write that hence these two are equal, but I am leaving it here itself. Next, the third one, if S and T are vector space homomorphisms from the space V into the space W, where we understand that V and W are vector spaces over the same base field of scalars, whatever that is, and VIS is equal to VIT for all elements Vi in some basis of V. For all elements Vi of a basis of V. If this is the case, prove that S is equal to T. This is almost obvious, but still for the sake of completion, let's write a solution. So we need to prove that S and T are equal as functions. So that means they must have identical effect on every vector from V. So let's take one vector. Let V be any vector in V. Then V is a linear combination of basis vectors, say alpha 1 V1 plus alpha 2 V2 plus alpha n Vn. Since it's already mentioned that Vi are they form some sort of basis for V, so we are not again mentioning that fact, repeating that fact. Note one more thing, that we are not assuming here that V is finite dimensional. No, we may actually be infinite dimensional, but still it has some basis, and from that basis you have this. Now at this point I should mention one thing. See, when we are doing algebra, usually we do not deal with infinite sums unless the construction of our algebraic system itself has an infinite sum built into its structure, which has to be interpreted in some specific way. Ordinarily, when we have things like this where algebraic operations are involved, we do not consider infinite sums. That's because if we do so, then question of convergence arises, and for that to be meaningful you need a topology. Such things should be there, but when we are considering something like this in algebra, simply just some elements and operations among them, then everything is finite. Now although you may have an infinite basis for V, from where actually these Vi's are coming, but when you take a vector in V, the statement that it's a linear combination of basis vectors means that only finitely many of those basis vectors are involved in that linear combination, because a linear combination by definition is a finite combination, even if your space is infinite dimensional. Okay. So what is V? Oh, we have, okay, let's just apply S first. Alpha 1 V1 plus alpha 2 V2 plus alpha n Vn S. Using the fact that S is linear, this becomes V1S plus alpha 2 V2S plus alpha n Vns, and then you use the given condition. Alpha 1 V1T plus alpha 2 V2T plus alpha n Vnt, and then again you use the fact that T is also like S, it's also linear. So in place of this sum you can write alpha 1 V1 plus alpha 2 V2 plus alpha n Vn T, which is nothing but Vt. So that's how Vs is equal to Vt, but V was chosen to be an arbitrary element of our space V, hence S is equal to T. You can, in fact, to emphasize the fact that V is arbitrary, you can explicitly write, since V is an arbitrary element of capital V, that's why S and T are identical as functions, or S is equal to T. Next, four, complete the proof with all details. with all details that home v comma w is a vector space over F. Over F, and we have already done this. Okay, we have done this with all details means we have done it absolutely elaborately, as elaborate as possible. So this already is there with us. Next, 5, the fifth one. If psi denotes the mapping denotes the map, ink the mapping in the text used in the text, same thing, the mapping in the text of V into V double hat that means the double well, that mapping give a complete proof that psi is a vector space homomorphism. Yes. Homomorphism of V into the second dual of V, and this is also something we have already gone through. Next, let's see another one. If V is finite dimensional if V is finite dimensional and V1 not equal to V2, these are vectors in V. Prove that there is an f in the dual space of V such that V1F is different from V2F, and in the solution we can, that means we are given a finite dimensional vector space V in which we have two distinct vectors V1 and V2. Then we have to prove that there is a linear functional under which the images of these distinct vectors are also distinct scalars. So here we can just directly use lemma 432 by, but before we before we use this lemma though, we need to make sure that its hypothesis is satisfied. Since V1 is not equal to V2, V1 minus V2 is a non-zero vector in V. So by lemma 432. In this lemma we have seen that if we have a finite dimensional vector space in which there is a non-zero vector, then the image of that non-zero vector under at least one linear functional is a non-zero scalar. That's what we have here. There is a linear functional f such that this image is non-zero, but this implies, because f is linear, V1f minus V2f is non-zero, or V1f is not equal to V2f, and that just completes the solution, and it completes this video also. Although it looks like we have solved 6 of the exercises, but most of them we already have done the work for these solutions when we were going through the theory. But anyway, it's all over. So in the next vector space update, we are going to see more of these exercises and their solutions. And the next update is on Friday, of course, and let's do number theory once again. So with that, I just wrap things up for tonight. If you want to say something, you can use the comment section below, or you can mail me. My address will be there in the description. The link will be given there. So see you on Friday with number theory. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.